आपकी जो immune system है that goes 75% down, उसकी जो capability है बीमारियों से लड़ने की। तो इसीलिए अगर आप एक आध रात ना सोए तो फ्लू जो है इट्स वेरी कॉमन। और क्योंकि फ्लू के जर्म्स हैं वो ज़्यादातर हमारे इन्वायरमेंट में है, तो इसलिए हम उन्हें वो हमें मिल जाते हैं। लेकिन उस एपिसोड के दौरान अगर if you come into contact with other germs, you're probably getting those as well. Let's say hepatitis, इस तरह की जो चीज़ें हैं, तो sometimes they are activated after several years. So नींद जो है it's affecting everything. और क्योंकि हम पढ़ते हैं, मेहनत करते हैं, सब कुछ ultimately for happiness in our lives, and happiness is not only directly proportional to the grades, it's proportional to several other things. So anyway, that's something that you have to decide. Okay, so coming back to the class, we have discussed so far the historical debates surrounding the nature of light and the velocity of light. The debate on velocity of light was settled quickly by several experiments where people measured speed of light in vacuum, in air, even in water and other substances. But the debate about the nature of light is actually still continuing in some ways. In 19th century, the debate was actually centered around the presence of ether, because people had come to believe by several experimental experiments and Maxwell's theory of electromagnetics as well, which was explaining almost everything related to electricity and magnetism happening around. And it was almost a given that light is an electromagnetic wave. And since a wave needs a medium to propagate, as most people believed at that time, there has to be some medium which is so light that we ordinarily are not able to feel it or detect it, but it's present, whose undulations or vibrations are causing propagation. So it became necessary to do some experiments to directly measure ether. There were some experiments which indirectly were explained by assuming an ether. For example, the refraction of light. Why is the angle of light different in let's say in water, when light goes to water? It's because it contains a higher density of ether than air. So it is denser, the speed is slower, so that's why we see the bending of light. Okay, so ether concept got a bit more complicated, but it was able to explain this natural phenomenon. But there were other experimental evidences that were coming up. For example, if you recall, Bradley was the person who discovered star aberration, that when he pointed his telescope on a star in this plane, he saw that he has to adjust the angle when the Earth is moving toward or away from the star. This experiment was done in early 18th century, and at that time people used to believe in Newton's corpuscular theory, and for that you don't actually need an ether per se, because these are particles that are coming from a luminous source and they're traveling, so you don't need a medium for them to travel, they can even go through it. And the star aberration actually was nicely explained by this theory, because you could use Galilean law of velocity addition that if you have something which is moving with a velocity v naught, and you are moving towards that object with a velocity u, the velocity that you will measure is given by v naught plus u. And since it was only one component of the light, for example, light is coming like this, we are doing like this. So this is the velocity of Earth, and this is the component of velocity of light in this direction. So this component gets modified, so this angle changes. But later on, Young actually re-explained the same phenomena using the wave theory, because he postulated that since everything is in ether and the wave is propagating in ether and we are moving in ether, so essentially a similar concept can be transported to wave theory as well. If we have a wave moving in a medium and we are moving with respect to that medium, the speed of the wave is that as it's going to be measured by this object is going to be different. So he explained the same star aberration using wave theory, and then there was another experiment by Arago in about 1801, and he wanted to see that if different stars measure emit light with different speeds, because if the light is made of particles, heavier objects would be pulling them harder towards themselves, so the speed of light would be different for different particles, for different sources, and not only the mass, but also different stars are presumably moving with different speeds in heaven. According to this Galilean velocity transformation law, the speed that we would be measuring for light emitted by different sources should be different, right? Because this V naught is actually different for different stars. So to do that, what he did, he said, okay, let me put a prism in front of the telescope. So the light is coming here, and since a prism refracts light, and refraction is proportional to the ratio of speed of light in this medium to this speed. So if the speeds here are different, and presumably the speed in the prism is same, so we would have different ratios, and the spectrum, diffraction spectrum would be different if he points the telescope at, let's say, sun or moon or other stars. But what he saw was that the spectrum is exactly the same. We have the same refraction from different sources of light. So this was a blow to Newton's theory, but this was also a blow to the wave theory as well. Because in wave theory also, if there is a medium and this telescope is moving in the medium, there's actually another problem, not this problem, okay, the light from different sources has the same speed, but let's do another experiment. In the lab, let's say we have a source of light, a white light source, and we put a prism, so we get a diffraction spectrum. And if this source is moving, then according to wave theory, this should be different, because the ratios of the speeds would be different. But when you point your telescope on a source in the lab, you still get the same spectrum as when you point it, let's say, at sun. So this was problematic for wave theory as well, because wave theory also predicts the same formula for velocity emission law. So what happened that there was this person Frenner that we actually discussed before. He postulated another thing about ether. Now so far we have two postulates about ether. First of all, ether is present everywhere, inside the body as well. The second modification was that its density is different in different medium, that's why the speed of light is different in different medium. Now the third modification for moving bodies comes from Fresnel. He says, let's assume that so this is already present. If let's say rho naught is the density of ether in vacuum, suppose, or background density, then the density of ether in material bodies is given by this, which is proportional to the square of the refractive index. With this assumption, you can explain that speeds are different in different medium because densities are different. Now, the trouble was arising because of this thing. Let's say we have a background ether, and then there is this prism in it. So this has this much density, and this background has this much density. If the prism is moving, what is happening? Is it carrying all of its density rho prime along with it, or it's not carrying? That should be it. That has to happen. If it carries all of its density along with it, then because when it goes here, the density here is different from the background, so it means that density has come from here. So Fresnel postulated that assume that it doesn't carry all of its density along with it, but only carry the difference. So the difference is rho prime. Oh. So this is the difference, which is equal to n squared minus 1. Oh. So he assumed that a body partially drags objects with it. And since it partially drags objects with it, the velocity addition law is not this, but it is this. That only a partial fraction of this velocity is affecting the speed of light in that. So the classrooms has been changed. Normally, what happens is this: if this is the speed, let's say V naught of something which is coming towards this prism. If the prism is stationary, let's say the prism measures the speed of light as V naught. If the prism, suppose, is moving in this direction with speed u, Galilean law of addition says that the speed of light measured by this prism is V naught plus u. But that didn't agree with the experiment. Fresnel proposed that instead of the speed being V naught plus u, the speed is only V naught plus u into this fraction of the ether is moving along with this body, and the fraction is the difference divided by the total density. So rho naught gets cancelled. So with this thing, he was able to explain that if you have a prism which is stationary, and let's say this is the diffraction that you get. So different colors goes in different direction. But if we assume that the prism is moving, let's say with speed u, he actually computed with this partial drag that if I now imagine that the speed of light in this medium is not, so when you have to compute this diffraction, the speed is in stationary prism is v naught. And if the prism is moving with speed u and you assume that the speed of light in the prism is this, and you compute how the wavefront gets transformed, like for example, the light, the part that is here goes here, the part that was here goes here, and you take into account this thing, you end up with a spectrum that is exactly the same that was for the stationary prism. So he explained this apparent diffraction by a moving prism, which is the same as by a stationary prism, by this postulate. So if we assume partial drag of ether, we end up getting the same diffraction whether the prism is moving or if it is stationary. So this was his hypothesis of partial drag. I'll come back to it later on how we can refute this hypothesis as well. And the crowning achievement of this hypothesis actually came later. So with this thing, you indirectly prove this hypothesis by this diffraction pattern, which is the same for moving and for the stationary prism. Physio did an experiment to directly measure the speed of light in a moving medium in water. So actually he measured speed in stationary water as well, but what he did, he measured the speed of light in moving water and found that that speed is exactly as is given here in this water. What he did was this. Let's say you have a source S and partially silvered mirror and a prism and a lens that makes it into a parallel beam. I'm not putting it here, but his main thing was these two tubes. Which has glass windows, but they have water in them. And then he has, so light travels like this. He has a focusing lens and then he has a mirror here. So the lens focuses the light to be here. So what happens that the light ray that comes here, strikes this mirror, is actually reflected in this direction and goes back through this path, goes back here and goes here, and the ray that's coming from this side is reflected here, goes through this path, gets back here and reflected here. So this is where he gets the image. So let's say initially the water is stationary in both tubes. So we have the image of this source at this point F with this object. Now what we can do is make the water move in this tube. Just have to have some pump which has, let's say, a tube coming out from here and a tube coming out from here, and you circulate the water between the two tubes in such a way that water moves in one tube in this direction and water moves in this tube in the opposite direction, simply to enhance the effect. So what will happen, that the beam, let's say that is going from this path, it's going in the same direction as the velocity of light. So velocity of water, so this goes here, gets reflected, and when it goes back, it's again in parallel with the speed of water. So the effect is multiplied and it gets back here and we have another image. So when water is moving, the image is shifted because the speed of light would be different. Would it be shifted? Actually no, there's not going to be the shifting of the spot. This experiment goes like this. So let's say water is stationary. So you have light coming here from two parts. Light going like this. One part of the beam is coming from here and the other part of the beam is coming from here. And they are going to interfere here. And if they are both in phase, we are going to get a constructive interference at this point. And since they are being overlapped over a wider region, so at some point they are out of phase and some other point out of phase. So we have a band of dark and bright bands. So we have a series of dark and bright bands when the water is stationary. Now, when the water is moving, again we have the interference of two beams of light. One which is going like this, which has traveled opposite to the speed of water, and the other beam which has traveled in along the same direction as the speed of water. If the speed of light is same in the stationary and moving water, nothing would happen to this fringe pattern. If the speed of light is different in moving water than stationary water, this fringe pattern will shift. Because now the constructive interference will happen at some other point. And by measuring the fringe shift, you can measure the speed of light in the moving water. So that's what he did. He measured the fringe shift and the change in the speed of light in water, and he knew the velocity of water. He put everything in here and it perfectly fits this one, which proves that Fresnel's hypothesis of partial drag of ether is correct. And these types of experiments and these types of prediction, they're actually called the first order effect of the presence of ether. First order because we are directly observing this effect. Ether is moving, something is moving in it, so the speed is changing, and we are directly observing this effect through the fringe shift pattern. So this is the first order effect of ether drag, which is confirmed by this experiment. And so this experiment was done around I think 1800 something, and these experiments and Maxwell theory, they were all setting towards this idea that ether is present, and so it has a partial drag when bodies move, and we are able to confirm the presence of ether. Michelson actually did another experiment to measure the presence of ether by second order effects. That what effectively what he did, I'll come to that experiment in detail. If you have a river that is flowing in one direction and you want to measure its speed, one way of doing is that you directly measure the speed, right, that this experiment is doing, or you can do what is called the detection of second order effect. You send a boat, you take two boats of constant speed with respect to the water that they are in at the moment. You send one boat perpendicular to the direction of flow and the other boat parallel to the direction of flow, and see how much time they take to go and come back to cover the same distance. If the time taken by the two boats is the same, it means the river is stationary. If the time taken by the two is different, it means the water in the river is moving in one particular direction. And if you happen to send both the boats perpendicular to water, you won't be able to see the effect. So one boat has to be perpendicular and the other boat has to be parallel to the flow. And if you don't know, you're blind that which way water is flowing, what you can do is you can send, say, one boat in this direction, the other boat in this direction, or two arbitrarily orthogonal directions. And then you can just rotate those two directions. And you take measurements over a 90-degree interval, and you will be able to conclude from that if the water is moving or not. And actually his experiment showed that there's no detectable ether, because the speed of light in both directions turned out to be the same. And so they disproved the ether hypothesis. And initially people tried to construct several other theories to actually explain Michelson's experiment. But there was one person who quickly took those results to be correct and quickly postulated one thing, that when you travel along the when you are moving in space, the length contracts along the direction of your speed. If you just assume this thing, you can still preserve ether and you can still explain Michelson's experiment, right? For example, if you are going along the direction of river flow and you assume that the length is now not the same as it would be in stationary water, you can prove that okay, water was moving, but I was able to go and come back in the same time as I was able to go and come back in perpendicular distance, because distances are now contracted. When I was moving along the flow, the distances were actually elongated when I was moving along the flow, and the distance is contracted when I'm moving off. So if you assume this contraction hypothesis, contraction of space, you can prove the null result of Michelson, and you can prove you can still preserve ether concept. Because ether was necessary for light to be a wave. That was the trouble. That's why people needed ether. Until Einstein came, who said, we don't need ether for light to propagate. Let's assume that light can propagate in vacuum. And from that, Einstein's special theory of relativity came into being. And but Lorentz contraction actually turned out to be true, by the way, but from different hypotheses as opposed to the ad hoc hypothesis of Lorentz that length contracts when you move. But his ingenuity was in his own right, that he simply postulated something that turned out to be true from another theory. So I'll come back to very important Michelson's experiment and Lorentz contraction later. But before, let me briefly discuss the classical relativity. And what does it mean? And so that we will be able to know how does the Einstein's theory modifies this. So classical sense of principle of relativity is actually to Galileo, but its essence has been present for almost as long as we can trace science. You see, we try to express the principle of relativity like this, that the laws of physics have the same form in all inertial frames of references. This is a very technical and jargon-filled definition. In essence, it has this belief incorporated in this principle that the laws of physics are same everywhere in the universe. The two charges attract each other with the same force and formula that they do on Earth, as they will do on Sun, on some star, at any stretch of universe. Not only anywhere in universe, but also at any time in the past and future life of the universe. That belief is why people have been trying to construct scientific theory from the very beginning to encompass everything in the universe. Stars, sun, moon, earth, humans, and everything. So in essence, this is this thing, that all the laws of physics are the same everywhere in the universe, at all time, starting from, let's say, the Big Bang towards the end of the universe. That's actually what principle of relativity means, which we can write in, the jargon-filled language like this, that laws of physics are covariant. Covariant means they have the same form. The quantities may be slightly different. For example, F is equal to ma has the same form here, has the same form at Sun, and in any other inertial frame, though maybe the force and mass and acceleration may have different forms, different values, but the relation is going to be the same. So any law, when some law has the same form in two different frames, we say the law is covariant. Invariant is something that doesn't change. If mass is 2 kg on let's say Earth, and it is 2 kg on Sun, we say it's an invariant thing. Similarly, any other quantity that doesn't change, it's invariant, and a law or equation that has the same form, though the definition of individual quantities may change, or their magnitudes or values may change, but the form of the law remains the same, then we say that the law is covariant. And that's what the principle of relativity is. That in inertial frames, the laws of physics have the same form. We can say it like this. Inertial frames are the frames where Newton's first law holds. An inertial frame is a frame where Newton's first law holds. Newton's first law is that the acceleration, if the acceleration of an object is 0, at one instant of time, it will remain 0 for later instants of time. Which means that if a particle has some velocity at some instant of time, let's say t naught, which is vx, vy, dz, it will remain so unless some force is exerted on it. So in the absence of any force, a zero acceleration will remain zero. So any frame of reference in which this thing is true, that an unaccelerated body remains unaccelerated, then that frame is called an inertial frame. Earth, to the first degree of approximation, is an inertial frame for our everyday things. If I have a chalk here, it seems to be like this. And similarly, other objects that we see, unless we consider this direction towards the center of Earth, because there's a force that is along this direction. But this frame of reference is kind of an idealized frame of reference somewhere in the universe where all the forces are zero and anything is there. So a zero acceleration initially will mean a zero acceleration at the end. So this translates into this thing that if something is moving in that frame, it will be moving along a straight line, because if it is unaccelerated, it cannot change its path. And if it is stationary at one point, of course it remains stationary. But inertial frames are not unique. There may be one frame, let's say X, Y, Z, where there's a body with coordinates X, Y, Z that has zero acceleration, but there may be another frame of reference which is inertial, that the acceleration of this point particle is zero in that frame as well. And let's say that inertial frame is x prime, y prime. So using the principle of relativity, we can drive a relationship between the coordinates measured by this frame and the coordinates measured by this frame. Now, there are two ways to transform the coordinates of this point from this inertial frame to this inertial frame. So one is an old way, which we will call classical or Galilean way, and the other is the one that is introduced by Einstein. You see, all of these troubles with the measurement of speed of light in moving frames were happening because people were transforming the coordinates according to a certain principle, v is equal to v naught plus u, which was modified by Fresnel to this thing, but the basic was coming from this. This is essentially the same as this velocity addition law, except that he only postulated that since only a part of the body is moving, maybe when we are using the velocity addition law, we don't have to add the full velocity of this body, but only that fraction of the velocity of this body needs to be added to v naught, which is the fraction that is moving. So, but essentially it was coming from that same thing. So we are going to drive that law right now, and we will see what are the assumptions that are underlying that transformation. Because we will again drive a transformation from one inertial frame to another inertial frame using the Einstein's theory of special relativity, and we will see that the underlying assumptions have to be changed, which actually relates to the notion of space and time. Because when in classical world, when people transformed the coordinates of the objects from one frame to another, they had certain assumptions behind it. And let's see what those assumptions are so that we can do the same derivations. So number one was this. So this essentially has time as parameter as well. So I will call them Galilean assumptions. Number one was this thing, that the time measured by both the frames is the same. And perhaps it makes sense because in those days, the speeds that we had were usually very small, and if a person is going on a horse, or somebody is walking, or somebody is stationary, the watches that you have in pocket, even though they came actually later than these assumptions by Galileo and Newton and these transformation, but essentially it seemed to be a very intuitive idea that the time is the same here and everywhere else. Essentially, perhaps it goes back to this conception of infinite speed of light as well. But anyway, so if we make this assumption that time is measured, the time measured by both frames is the same. So this is the first assumption. The second is that distances measured by both are same. If we have 2 points and you measure distance either in this frame or in that frame, the distances measured by both frames are the same. This was the second assumption. The third assumption was that they are inertial frames. Okay. So this is inertial, this is inertial. And inertial means that if a particle is moving, so if this one sees its trajectory, it should be straight line. And if, since this is also an inertial frame, this should also see the trajectory to be straight line. So I can write it in several ways. Either I can say that both frames are inertial, or I can say that the trajectory of a particle is a straight line. It means the same thing. If it is unaccelerated, its trajectory is a straight line. Now to find the transformations between these coordinates and these coordinates, so first of all, this thing p prime is equal to t is defined by assumption as well. But other, let's say x prime is some function of x, y, z, and t, and y prime is some function of these coordinates, and z prime is some function of these coordinates. So what is the possible form of these functions based on these assumptions? Can these functions be nonlinear? Why?
Because of the third assumption.
Yes, because of the third assumption. If it is a straight line in one coordinate, and for it to be a straight line in the other coordinate, the relationship between primes and x, y, z, not the t. T can still be nonlinear for this assumption. It has to be linear relationship. Only then a line in one coordinate system goes to a line in the other coordinate system. Can it be nonlinear in T? No, because it again gets to two things. That it has to be straight line plus t prime is equal to t time is same in both coordinates. So it has to be, and also if the distances have to be the same, the relationship has to be linear. So the most general transformation from x, y, z to x prime, y prime, z prime is of this form. This is going to be a bit complicated, so let me explain one more thing, that this coordinate system in general is not aligned with this coordinate system. So let's say this x-axis makes an angle, let me put just for angles, let's say this is the x prime axis of this coordinate system. Let's say the angle of this axis with this is x prime, and the angle of this axis with this is y x prime, and angle with z axis is z x prime. So this axis makes three angles with these three axes. Similarly, this axis makes three angles with the three axes, and this axis makes the three angles with these three axes. So the x prime coordinate in this coordinate system depends on all these three angles, on all these three coordinates, because the axes are tilted. And I'm going to do actually the harder way initially, then I'll do it using vectors, and that will be very intuitive. But let's do it in a difficult way initially. So x prime, first of all, it depends on x, and since it depends linearly, let's say x naught, y naught, z naught is the position of the origin of the second coordinate system at time t is equal to t naught. So you see, the origins do not have to be at the same point at t is equal to 0, but in general we can assume that at some time t naught, the origin of prime was at this point. So then x prime is x minus x naught, and let's say that the x prime, y prime, z prime, its origin is moving with velocity ux, uy, uz. O prime is moving with this velocity. So the origin is translating with these three components of velocity. Then x prime, if it would have been stationary, x prime would have been equal to this if both axes would have been collinear. If x prime and x are in the same direction and then that t is equal to t naught, x prime would simply be this. But since it's translating in time as well, so there is another component. So what you can imagine it like this. This is the x coordinate of the point, and this is essentially the coordinate of the origin at time t is equal to t. At time t is equal to t naught, the origin was at x naught, and at a later time t, the origin has moved by this much, so you have to subtract this thing from x. And since x and x prime are not linear, you have to multiply it with the cosine of the angle between x and x prime. So plus, there is a term from the y coordinate, cosine of the angle of y axis with the x prime axis, cosine of essentially, this point has x, y, z components. What you do is take the projection of this vector, which is x prime, y prime, z prime, along your three axes, and this is what you get. So this is the projection along x, y, and z axis. Everybody's okay with this thing? Essentially, I'm assuming that origin is moving away from this thing. So then it is added, and if you assume that u is in some sense coming towards origin, then you put plus, but we can assume one thing, and if u is negative, it will automatically be plus. If u is positive, it is positive. So ux, uy, uz, these numbers can be plus minus independently. Okay. Similarly, y prime boring है, but let's do it because it will be useful later on. Z prime is so there are 9 different angles that are involved. So if the both system would be collinear, this would simply be equal to this. This is 1 because x prime is 0, so there are no these terms. Then it's easier to understand. Then y prime would only be equal to this because this is 0, these are 90. So these two terms go away, and z prime would be equal to this. This is cosine. Only this term. And if the system only has, let's say, ux, and it's not moving along y and zx, so then only this term would be here. This is 0, and sorry, this would be 0, and this would be 0. So then it would be even simpler. Again, ये जो है, this is the most general Galilean transformation of coordinates that I have written here. Now from this coordinate transformation, which are based on assumptions about space and time. Assumption about space is this, that the distances measured by the two inertial coordinate system are equal to each other, and the time measured by the two is also equal with each other. So based on, and of course they're inertial, so straight line has to be straight line. Based on these two assumptions of space and time, this is the most general transformation of space coordinate. I haven't written the fourth equation because it's already written in p prime is equal to t. Now we can find out the velocity transformation law. And to do that, all I have to do is simply take the derivative with respect to time. So x prime dot, the velocity in the prime coordinate system is simply x dot. So this is constant, 0. So the derivative of this thing would be with respect to time. So this term will have 0 derivative. क्योंकि t naught भी constant है, ux भी constant है. So इस term का जो derivative है वो simply होगा ux y dot minus uy cosine plus z dot minus uz cosine z x y dot is y x dot minus ux. Angle is changed to x y prime plus y dot uy cosine y prime plus z dot minus uc cosine zy prime. Equations book में लिखे हैं, don't have to write them if you don't want to. X y, sorry, this x dot minus x. I used to tell people that they don't have to write the lecture, just concentrate on understanding, but over the years I have learned that perhaps for some people writing is same as understanding, so it's up to you what you want to do. Cosine y z prime z dot uz cosine z. So this is actually the general coordinate, general transformation of the components of the velocity. Now we can see if the two frames are inertial or not by taking another derivative and seeing if a zero acceleration in one gives us the zero acceleration in the other. And to find the acceleration transformation law, I can take another derivative, x double dot. So its derivative is 0, so we only have x dot cosine x prime, y double dot cosine y x prime, z double dot cosine z x prime, x double dot cosine x y prime, cosine y y prime, cosine z y prime, x double dot cosine prime, cosine. So you see, if x double dot and y double dot and z double dot are 0, these three are also 0. So the way we have written it indeed preserves the Newton's first law in both the fields. So let me do it, these transformations using vector calculus, and you will see why vectors were invented. These were the times that people actually did have vectors came to be in real use in physics actually only 100 years ago. Before that, people used to work only with scalar equations. Even Maxwell's treatise in electrodynamics is with scalar equations. Anyway, so let's try to derive it using vectors. For that, let's say the origin of this dash coordinate system has coordinate r nav dash. And let's say the position of this point in the original, actually there is no original coordinate system, but in the unprimed coordinate system is r, and its position in the prime coordinate system is r prime. So in this case, as you can see, vector addition law, r should be equal to r naught dash plus r dash or r prime.
Sorry, can't see.
Yeah.
Can't see.
Let's do it with yellow. So the position of the origin of the prime coordinate system with respect to the unprime coordinate system, let's say this is r naught prime. Okay? And the position of this point with respect to the prime coordinate system, let's say it's r prime. And the position of this point with respect to the unprime coordinate system, let's say it's r. Which means that from vector addition, we can see that this should hold. R naught prime plus r prime should be equal to r. Right? And what is R naught prime? R naught prime is R naught. R naught is the position vector of O prime at t is equal to t naught. So what's the position of the O prime origin of the prime coordinate system at some later time t? It's R naught plus u into t minus t prime t naught. Okay. This is O, this is everybody's okay with this?
उसमें R naught
R naught जो है वो पोजीशन है O प्राइम की, ये जो ऑर्डिनल है at t is equal to t naught. ठीक है. तो at later time t इसकी पोजीशन क्या होगी?
U और
R naught plus u is the velocity of that point. So simply u into time interval, right? So this is the distance covered by O prime in this time interval. So the general position of the origin of O prime is this. So let's put this thing here, and we get R equals R naught plus u t naught plus R prime. So what is R prime? R prime is R minus R naught minus u into t naught. And you can see this is exactly the same as this thing, except that you can't directly see it. This is in abstract vector notations, and this is in component forms. But we can quickly get these components if we want. What is x prime? X prime is nothing but the component of this position vector in the prime coordinate system, right? If you have some vector R prime and you want its component along x-axis, all you have to do is take its dot product with a unit vector along this axis, right? And what is x hat in terms of this coordinate system? X hat prime is, let's find the components of this unit vector x hat prime in this coordinate system. And let's say this is angle xx prime, so its component along x-axis is cosine xx prime. Its component along y-axis is cosine yx prime, and its component along z-axis is cosine zx prime. Right? ये जो x unit x hat prime unit vector है, इसका component तीनों axis के along simply cosine of this, क्योंकि unit vector इसके magnitude 1 है, तो 1 into cosine this, 1 into cosine this, 1 into cosine this angle, and you replace.
लेकिन हम कम भी कर सकते हैं, मतलब x x और y x रिलेटेड ही है ना, तो sin होगा, तो cos y x sin x x prime हो जाएगा.
इतना सिंपल ही, अगर तो आप दो एंगल्स में करना चाहते हैं, then it has, let's say angle theta and phi. Then you go in spherical coordinate system. तो सिर्फ एक एंगल जो है वो कोसाइन से, फिर you take the projection in this plane, the sin into cosine, थोड़ा सा complicated हो
लेकिन मैं
जाता
कह रहा हूँ x x prime plus y x prime equals 90, ये तो वहीं से नजर आ रहा है. x x prime plus y plus y x prime equals 90.
नहीं ऐसा नहीं है.
ऐसा नहीं.
ये देखो
वहाँ से y से आप
ये x है, ये y है, ये z है और ये पॉइंट है. सो ये लाइन इसको जॉइन करी तो ये एंगल एक डिफरेंट प्लेन में है और ये एंगल एक डिफरेंट प्लेन में है.
अच्छा
ठीक है, तो तीनों एंगल जो है वो डिफरेंट प्लेन्स में है.
अच्छा
ठीक है, क्योंकि लाइन जो है वो u करके है. एक एंगल u है और एक एंगल u है और एक एंगल u. ठीक है, इसीलिए हमें u लिखना पड़ रहा है. अगर हम वेरिएबल कम कर सकते थे, कम कर सकते। अब अगर आप इसका इसके साथ डॉट प्रोडक्ट लें, यू गेट एग्जैक्टली द फर्स्ट इक्वेशन ओवर देयर। ठीक है कि x हैट का डॉट होगा इसके x कंपोनेंट से, so rx r का x कंपोनेंट x है, r नॉट का x कंपोनेंट x और u का x कंपोनेंट ux है। सिमिलरली फॉर y कंपोनेंट इसके y के साथ ये वाला पार्ट आ जाएगा, इसके z कंपोनेंट के साथ ये वाला पार्ट आ जाएगा, you get the first equation. Similarly, y prime you can get there and z prime you can get there. And now let's see the velocity transformation law using vectors. Velocity all I have to do is take a derivative with respect to time. So इसका time derivative आ जाएगा r prime r dot, r naught का derivative 0 हो जाएगा और minus, so this is the Galilean velocity transformation. And if we take another derivative, we do see that the accelerations measured by both have the same form. The components of the acceleration, which are actually physical quantities. Remember, vector is not a physical quantity. Vector is a notation or a symbol or an abstract thing whose components are physical quantities. The three physical quantities associated with acceleration in the prime and the unprimed coordinate systems are different because x double prime is different from x double dot prime is different from x double dot. But the form is same, and so to say you can say the acceleration in both of them is the same. It's better to say the acceleration has the same form in both coordinate systems. Acceleration is covariant. And if we make an additional assumption that mass is invariant between the two inertial coordinates, this is an additional Galilean assumption. If mass is assumed to be invariant between the two inertial frames, what we get is this. So Newton's law have not only the same form, but the force is also the same, the vector force is the same. The components of the force measured by the two would be different because they're oriented differently, but the force is the same. And actually, but we can see that if they are oriented linearly, even if they are moving, they would measure the same acceleration along three axes. Because then this is 1 and these things 0, so x double dot prime is simply equal to x double dot. So what I want to stress actually in this part is this: if you make certain assumption about space and time, you get a certain relationship for transforming not only the coordinates but also the velocities and accelerations. And we will see how the gravitational law transforms under Galilean transformation. It actually transforms covariantly. And then we will discuss that these assumptions which leads to these velocity addition law were actually coming in contradiction to the experimental results. And that's why initially people tried to devise ad hoc hypotheses, Fresnel's partial drag, Lorentz length contraction. And there are actually many other theories about emission, that when a body is moving, it emits lights, maybe it's emitting with a speed c that is independent of light, and various other assumptions. Einstein actually sidetracked all those ad hoc assumptions because they were all trying to preserve these assumptions. He actually changed these assumptions. Even though his theory gave the same Lorentz contraction as Lorentz just ad hoc Lorentz proposal ad hocism, but his theory was more famous on, it's considered to be theory than Lorentz because it's based on a revamp of the system, the way we think about space and time. So we'll continue with this thing in the next lecture. So